Okay, to wrap up this first section of our new unit, we're going to take a look at one of the major themes, and that is called combinatorics. Well, combinatorics is a branch of math that deals primarily with counting things. We could count big sets of things. We could count small sets of things. You can count individual objects. Counting really anything. That could be sets. That could be individual objects. Could be counting outcomes, which is what we'll focus on. You can count sets of sets. You could count sets of sets of sets. There's really no limit to what you can count. It's basically just counting. A couple of keys. Number one, we don't want to double count things. Can't count things twice. And we also don't want to miss anything. We want to make sure that everything we're trying to count gets counted one time and only one time. This sounds fairly simple, counting things. And it is, for the most part, fairly simple. The tricky part is going to be interpreting what we can and what we can't include when we count. And another tricky part is don't double count. Those are usually the two places where mistakes will be made. Not reading and understanding the problem thoroughly enough and double counting. As long as you avoid making those two mistakes, this will be a fairly straightforward half unit. Let's look at some examples of what are considered basic combinatoric problems. I say that 10 times fast. We have a restaurant. Go figure. I would have a restaurant problem to start us off. And this particular restaurant, Red Robin, has 7 appetizers, 12 entrees, 5 desserts. We're going to choose one of each. How many meals can we create? A couple of ways to think this through. We could go ahead and list every single possibility of appetizer, entree, dessert. That would give us a sample space, and then we could count all the objects in that sample space, all the objects that have one of each, and that would take a great deal of time. I'm going to look at it from a slot perspective. I'm going to think of each slot as a decision that has to be made. The first slot will be my appetizers. The second slot will be my entrees. The third slot will be my desserts. Here I have 7. I have 7 choices to make or to choose from in this one decision. My second decision, I have 12 choices. My third decision to make is to choose among 5 desserts. Slot problems, as we said earlier, are all multiplication. So I'm multiplying 7 by 12 by 5, and I believe that comes out to be 420 different meals. There are 420 different possible outcomes here with these 3 decisions. And if that seems kind of high, remember that I have, just choose an appetizer. I'm going to choose one appetizer that has 12 different entree possibilities and 5 different dessert choices. So let's just pick an appetizer. I don't know, chicken, mozzarella sticks, Red Robin burger, piece of chocolate cake, Mozzarella sticks, different burger, chocolate cake. Mozzarella sticks, third different kind of burger, chocolate cake. And so on and so on and so on. Just running through those alone gives me 12. Then I change the dessert and run through all of those again. Well, that's 12 more. And then I change a dessert and run through those again, and so on and so on. Then I change the appetizer and then change everything else one thing at a time. And it doesn't take too long for that number to get up there fairly quickly. Next example, buying a car. Something that many of you are going to experience someday, and all the fun and paperwork and haggling that entails. It's a great way to spend a day of wasted time. We have all these different option packages, and let's say you're going to choose one of each to customize the car the way you want it. We have different colors on the outside, colors on the inside, different trims that go around the car, and then 5 different rim styles for your wheels. Because we all know that everybody cares about what your wheels look like. So, 4 basic decisions to make. Means we have 4 slots. I have 6 different choices for that decision. The next decision I make, I have 4 choices. The next decision I make, I have 4 choices. The last decision I make, I have 5 choices. Multiplying all those together gives us a total 480 different ways to customize your car. Slot problems, or the slot method, allows for a very quick solution to many of these problems. Next problem. There just so happens to be 14 of you in this class. Actually, I lied. There are 12 of you. Well, let's say there were 4. I'll change it. Got my classes mixed up here. Not the first time that's ever happened. 12 students in class. How many ways can I create a seating chart? Assuming that the world was back to normal and I can see you all, your bright, happy, smiling, shiny faces. And I'm not talking to a computer screen anymore. How many ways can I create a seating chart for a class of 12? Well, here slots aren't the best way to go. That's a lot of slots to fill in. So I'm going to be a little more clever on this one. I'm just going to fill in a few to see if I can find a pattern. For the first desk, the first slot will be desk number 1. There are 12 students that I have to choose from. And then somebody occupies that seat. So now there are 11 students to pick from for the next desk. 10 to pick from for the next desk. And so on down the line. 9, 8. Wait a minute. This looks like a factorial. In fact, it is 12 factorial. Every time I make a choice, my options are dropping by 1 every single time. It's a good thing you saw the factorial video before you got here. And this is going to be a very big number. There are 479,001,600 different seating charts I could have made at the beginning of the semester. 479 million for a class of 12. And you're not even the biggest class. You're actually the smallest class. Which means, yeah, a lot more choices, a lot more possibilities as the classes get bigger. A class size of 12, 479 million. And again, that seems way, way, way too big. But if you think about it, if you imagine everyone laid out in one arrangement, take one student and move them around the room. You just made 11 more seating charts. Now take a different student, move them around the room. You've made 11 more seating charts, and so on and so on. Now take two students at a time and switch them at all the different possible seats. And there's a lot of possible two-student pairs to move around. Then take a group of 3 students and put them in every single change possibility. And as you think about that, the number of possibilities is going to grow rapidly. And then when you're all said and done, when you've made every single possible change, yeah, you're going to be up at that number. A couple things to notice with this. We can still use the slot method. But because our options are always dropping by 1 every single time, a factorial is what we're going to end up going with here. Compare that with what happened on the last 2 problems. We went from 7, then we increased to 12, then we dropped to 5. 6, down to 4, or stayed at 4, up to 5. But there's a difference between these problems. In this problem and this problem, the number of choices here has nothing to do with the number of choices here. The number of decisions or number of choices here, completely separate from the number of choices here. The same thing down here with the colors. Each of these represents something completely different. They are not related at all. On this problem, every decision I make here affects what happens next. A decision I make here affects what happens next. All of these decisions are related to each other, which is why the choices keep dropping by 1. Whenever that happens, we're going to have a factorial. Whenever our choices drop by 1 every single time, look for a factorial. Final problem. License plate creation. Something that states have to deal with from time to time, especially when their population has an unexpected growth phase. They get more people than they're expecting. They have more vehicles being registered, and all of a sudden they start running out of license plates. For example, Wisconsin a few years ago had to add a 7th possibility on many of their license plates because they were starting to run out of possibilities. Something that we'll look at later on with telephone numbers and other things. This example, we're going to create a plate that has 5 spots. And we're going to look at the possibility of 2 letters followed by 3 digits. One thing we need to keep in mind here, letters. Capital or lowercase. That will make a difference. Capital letters, we know there are 26 in the English alphabet. License plates, I have never seen a license plate with lowercase letters, so we will assume uppercase only. When we get into the problems involving password creation later on, we may have to consider upper and lowercase. So then that's going to increase our choices to 52. But for this problem, we'll stick with 26. So I need a letter, and then I need another letter. And that brings up another question. Are we allowed to repeat letters. In the case of license plates, yes. So instead of 25, I'm still allowed 26. I might have QQ123 or GG555. Repeats are possible. Digits. Well, there are 10 digits. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 choices. Repeats are implied to be allowed. 10 choices, 10 choices, 10 choices. One of the things you need to figure out, and I mentioned as a potential difficulty, is you need to sort of read into these problems a little bit, but not too much. This is where real life experience is going to help. Hopefully, you've all seen license plates and have at least know a little bit about license plates. There are other real world things that are going to come into play. Is you're going to have to determine, are repeats allowed? Are certain types of numbers or letters allowed? Those are all experiences that you need to start thinking through as you do some of these combinatorics problems. And that's going to get into, are you allowed to count certain things? Are you allowed to ignore certain things? Those are all experiences you have to think through for yourself. You should know the basics of license plates. You should know the basics of password creation and so on. These are some of the things that, quote, you should know, unquote, at this stage of life. So that's going to make the problems potentially a little tricky for you. Is you're going to have to sort of know the rules, know the acceptable and unacceptable things in each particular context. Multiplying all these numbers out, notice we have 26 squared. In this case, we get 676,000 possibilities. 3 letters, followed by 2 digits. I have 5 slots, but I'm not sure that I really need them in this case. 3 letters, 26 times 26 times 26. That'll give me 26 cubed. Followed by 2 digits. So if I go 26, 26, 26, and then 10 possibilities, 10 possibilities, it's going to be 26 to the third times 10 squared. Now we're over 1 million possibilities. By simply changing one of these digits into a letter, we almost tripled the number of possibilities. This last one, any combination of letters and digits. Well, I have 26 letters to choose from, 10 digits to choose from. That gives me 36 possibilities here. I'll have the same 36 here, 36 here, and so on. Gives me 36 to the 5th power. Which is the largest of them all. Over 604, actually over 60 million possibilities. Those are some of the basic examples. Make sure you do the completion quiz that follows this. Make sure to submit it and post any questions you might have.